have seen what is threshold. Now we will see why there is threshold at all. Why there should be threshold? For example, you consider the same piston and cylinder type pressure gauge. We have got a piston and cylinder and piston rod, pointer and the scale. This is instrument. And why there is the threshold for this instrument? If you analyze, you can easily find that there should be some increment in the pressure P, say Pi. There should be some increment to make the point, to make the, say I will draw it a little better, piston nearer the cylinder. So make the pointer to make the piston move within the cylinder, the piston has to overcome the friction force. Say whenever there is a relative motion between two bodies, there is friction between any two relatively moving bodies. Now the piston has to move within the cylinder with reference to the cylinder. So if you want to make the piston move, the piston has to overcome the friction force between the piston and the cylinder body. So suppose Ff is the friction force, then until Ff is equal to the area A into delta Pi, the until this happens, until delta Pi is there, that is an increment in Pi is there, which when multiplied by area is equal to friction force. Until this moment, there will not be any motion for the piston. The moment the pressure increase higher than delta Pi, then friction is overcome and the force is acting in this direction, and that force compresses the spring and the piston moves as a whole. So there is a need for increase in delta Pi. Until that is between 0 to delta Pi, there is no movement of the piston, hence no movement of the pointer. So to make the pointer move from 0, we have to increase the pressure from 0 to delta Pi. So we call it this delta Pi as threshold value. So this is the reason why threshold exists in all instruments. Similar reasons are there for other type of instruments. That is threshold. Now the next concept is resolution. This is threshold what you have continued, and now it is resolution. Now the definition for resolution is the minimum requirement in input signal, that is minimum requirement or I will call it minimum change in input signal to make the pointer move, from any non-zero point. That is definition. That is, suppose the instrument is functioning somewhere in say Pi and say Pi or okay, I will call it Xi and Xo. Suppose this is the ideal relation, and now threshold, due to threshold the increment is there only after some delta Xi. So somewhere here, suppose this is operating point, at certain time this is your Xo1, and to make the pointer move from any this is a non-zero point, 0 is here, this is a non-zero point, from any non-zero point to make the pointer move, we have to increase the input from increase input by say another delta Xi, and suppose it has to fall, it has to reduce, then you will find it comes here. That is in case of the same instrument, if you want, when the pressure drops from a certain Pi1, and to make the piston move further, backwards, again the friction for this to move in this direction. So friction will be acting in opposite direction. Always piston acts opposite to the motion. So friction will be acting in this direction. To overcome this, we find there should be some drop in pressure Pi. Then only the spring will push it backward. So that much delta Xi is required. So delta Xi, say 1, we will call it 1, delta Xi 1. that is minimum change in input signal, that is delta x1, to make the pointer move from any non-zero point, either from a particular operating point below the point or above the point. There should be some minimum change in input signal, so that the instrument pointer moves from the indicated position, from any non-zero position. So to say, you find there is some relation between the threshold and the resolution. What is threshold? Threshold is the minimum change to make the pointer move from 0 point, whereas resolution is the change required to make the pointer move from any non-zero point. That means the commonality is resolution and threshold indicates minimum change in input signal. One is from 0 point, another is from non-zero point. So you can define one concept by the another one. That is, what is the change required to make the pointer move from any threshold value any non-zero point is resolution, and resolution at 0 point is threshold. That is, using one concept to define the another concept. Threshold at any non-zero point is resolution, and resolution at 0 point is our threshold. And in digital instruments, you will find resolution is this is for the analog instrument. This is for analog instrument. Whereas for digital instrument, difference between consecutive readings, that is your consecutive readings, that is the resolution for the digital instruments. That is, for example, in a pressure gauge, digital pressure gauge, reading is shifting from 1.1, 1.2, 1.3 and so on. So the difference between any two consecutive reading is 0.1 bar. So resolution is 0.1 bar. That is resolution. That means in digital instrument, resolution and least count both are same. In digital instruments, that is the property. The resolution and least count both are same in digital instruments. So next concept is precision and accuracy. Precision and accuracy. That is the next concept what we are going to see. These two terms are very important in the subject of measurement. Ordinary mechanical engineer or ordinary engineer may not make the difference between these two terms in measurements. They represent two different quantities in measurements. Though they look alike, but they represent two different things. To understand these two terms properly, we will take an example. Before that, what the two terms indicate. Precision, when we say precision of an instrument is plus or minus 1%, actually it is not precision plus or 1%, actually it is imprecision. Imprecision of an instrument is equal to plus or minus 1%. To indicate imprecision, we normally say precision is plus or minus 1%. This is a colloquial way of expressing things. It is accepted. Similarly, when I say accuracy is plus or minus 2%, it is not accuracy plus or minus 2%, it is inaccuracy. Inaccuracy of an instrument is equal to plus or minus 2%. So by using the positive term, we indicate the negative things. So by accuracy, when I say an instrument has an accuracy plus or minus 2%, actually we mean to plus or inaccuracy is plus or minus 2%, but accuracy for an inaccuracy of 2%, accuracy should be 98%, but we don't say like that. We simply say accuracy plus or minus 2% to indicate inaccuracy is plus or minus 2%. Yeah. Now, to understand these two terms, imprecision and inaccuracy, let us take an example. There is an instrument, again we will have the same instrument pressure gauge. It is very handy to explain the many concepts. Say we are conducting an experiment or a process, so to say a calibration process, in which say I got this pressure source and this I connected to a standard instrument, call it a standard instrument, where I can get the correct reading, standard instrument. Simultaneously it is connected to our instrument under calibration. This is instrument under study. Instrument under steady. This is an instrument under steady, and say for example now we have got some 50 bar as the instrument shows a 50 bar in the standard instrument, and we are taking readings in this instrument under steady. So morning and say 10 o'clock, 12 o'clock and 2 o'clock, 4, 5, see different timings we take, and we keep always the pressure here always 50 bar. And what are the readings shown by these instruments that we are interested? So for example, readings are like that: 51 bar, 52 bar, 53 bar, so 52, like that. The instrument is showing at different timings, these are the readings. So if I plot, it may look like this. So this is time at different time, and this is our PO, output of the instrument under steady, and our standard constant input is 50 bar. This is 50 bar kept constant, but the instrument is showing at different times different readings. So 51, so 52 and 53, and another time 52. So that is that. So the readings are spread over in course of a day. Now for this instrument, once you have taken such readings by using the instrument, you can easily compute or find out what is imprecision of the instrument, what is inaccuracy of instrument. For that, this experiment is conducted. What is definition for imprecision or precision? Precision is the capability of the instrument. Precision indicates, so to say, indicates the capability of the instrument to reproduce a reading. This is the definition for precision. Precision indicates the capability of the instrument to reproduce a reading. What is reading to reproduce? It's supposed to reproduce 50, or it's supposed to reproduce some, say it has shown 51 and 52, 53, 54. So different times, 2 times 52, other time different readings. So to say, the precision indicates the scattering of the readings. Even the input remains constant, how the readings are scattered. So the scattering, to understand the scattering, we should around which point. So we have to find out the average. This is the average. 52 is the average. This is theoretical. So I will say P theoretical. This is theoretical value, P theoretical, and this is PO average. This is PO average. That is our average is 52, because having 52 constant and one less, one more, one time more. So that 52 is the average. So scattering of the, or I will say the imprecision is given by the equation x measured minus x average or divided by x average into 100. In a set of reading, we are supposed to, now it is set of reading, we have got four readings we have taken. In this reading, the maximum deviation we have to find out, that is maximum deviation, magnitude of the maximum deviation, x measured minus x average divided by x average. If it is single reading, then x average does not exist at all. If exists, so here for a group of readings only it is valid. So we find the maximum deviation from the by either positive side or higher side or lower side, it does not matter. That's why we have put the magnitude of the deviation. So here in this instrument, x average is 52, the x measured maximum deviation is say 1 bar. So this, the whole thing comes as 1 bar. 1 is the maximum deviation by 50. Now the average is 52 and it is 100. So percentage. So this is equal to approximately 2%. Approximately 2%, and it is customary habit, or it is customary in the field of measurements, put always plus or minus. Sometimes the deviation is positive side, sometimes negative side, and take the maximum whichever is there and put that limit on both side of the on both sides. So to say, we are supposed to put plus or minus. After computing, put add, it may be a positive, but it may happen in some other time, it may also happen in the negative side. So always you put minus also, plus or minus. This way we are supposed to write the imprecision. So for this instrument, for this behavior, imprecision is plus or minus 2%. Now what is the inaccuracy of the instrument? For this, the definition says inaccuracy indicates the maximum deviation from the true value. Now note the difference between the definitions for imprecision and inaccuracy. Imprecision is the deviation from the average value, whereas inaccuracy states the deviation from the theoretical value or true value. So true means theoretical. This is true means theoretical value. So that is the main difference. The inaccuracy always refers to the true value, and the imprecision refers to the average value of a set of readings. Now here what is it? Inaccuracy is equal to, in terms of equation, inaccuracy is equal to x measured here PO are the x measured quantities, x measured minus x theoretical or true, whatever it is, that is maximum in a set of reading, maximum value, maximum deviation from theoretical in a set of reading divided by x theoretical into 100. In terms of percent, we always put, as we have done for imprecision, plus or minus. So for this instrument, the maximum deviation x measured minus x theoretical will be, so 53 is the maximum reading, because 50 is the theoretical value and 53 is the maximum. So deviation is 3. The maximum deviation is the maximum difference is 3. So plus or minus 3 divided by x theoretical 50, because that reading is obtained from the standard instrument. 50 is always the theoretical value. It is maintained constant. So it's theoretical value into 100. So this is equal to plus or minus 6%. Now you note the difference. See, for the same instrument, you got two different quantities. For this from this experiment, the instrument has got an imprecision of 2% and the instrument has got inaccuracy of plus or minus 6%. Now that's how this example makes very clear that imprecision and inaccuracy are not same. They are two different things. Now, having seen the difference between the imprecision and inaccuracy, you will see how the difference is coming between the inaccuracy and imprecision. Now, for imprecision, the source is elements within the instruments. What does it mean? The main source for imprecision is the available errors in the elements within the instrument. We know an instrument is made up of many units, basic functional units like transducer, transformer and so on. And when they were manufactured with certain errors, they will contribute towards imprecision. And what is inaccuracy? Source of inaccuracy. Inaccuracy is obtained from all elements within the instruments plus atmospheric conditions and nearby power lines, mounting conditions and so on, etc. So the source for inaccuracy is not only elements within the instrument, but also the other conditions outside the instruments give rise to inaccuracy. Now for inaccuracy, source are more and imprecision only elements within this. That's why we got 2% smaller value for imprecision, and inaccuracy we have got 6%. That is always larger. You find in an instrument inaccuracy is larger than imprecision, but by the process of calibrations, so called static calibration, if we reduce the error sources from other sources, then what will remain? Only elements, the error due to elements within the instrument, because we cannot change the elements within the instruments. Once your instrument is manufactured, later on changing the elements within it is not possible. So by process of static calibration, what we normally achieve is the higher value of inaccuracy is brought down to the value of imprecision, and reducing below imprecision is not possible. That is, it is decided by the elements you have selected at the time of design and manufacture. So this is the sources, and sometimes you find inaccuracy is given in terms of what you have, in terms of theoretical what you have got it. But another definition for inaccuracy is, so inaccuracy is equal to, in terms of full scale reading, inaccuracy is equal to x measured minus x theoretical. Note the difference is x measured minus x theoretical, not x theoretical minus x measured. It is not used for definition of inaccuracy. Divided by, instead of x theoretical, we say full scale reading. It is called full scale reading. Full scale reading. This also in practice, by full scale reading, always the error is referred to full scale reading into 100%. Always put plus or minus. This is another definition for inaccuracy, where it is referred to not to theoretical value of that particular reading, but it is the full scale reading. Inaccuracy, it is there for one reading or a group of reading. If it is a group of reading, it represents the maximum difference. Maximum difference. If it is a single reading, the single reading measured value minus theoretical value divided by the full scale reading into 100. So this will be the error for that reading. So this is all about imprecision and inaccuracy. Next is nonlinearity. Next is nonlinearity. So to say, I will call it linearity. Actually, it is called linearity. Linearity. As we have seen for accuracy and precision, the negative term, the accuracy represents inaccuracy, and precision represents imprecision. Similarly, here the linearity actually represents nonlinearity. When we say linearity is equal to plus or minus say 3%, it means nonlinearity of the instrument is 3%, not linearity. So same way here also colloquially we are using the word linearity to indicate nonlinearity. So to understand nonlinearity, we have to do a different type of experiment. Probably you can assume the same setup where pressure is given to two instruments, one is standard instrument, or where we read the actual value. The other one is the instrument under steady. Such a setup, but instead of keeping the input signal same as 50 bar, here what we are going to do, we will change the input signal or pressure from 0 onwards. This is the little change in the experiment to understand the phenomena or concept of linearity. So we conduct suppose the instrument is supposed to be linear. Yeah, suppose linear. This is a characteristic of the say xi and the xo. And xi or pressure is varied from 0 to maximum value. It can vary. This is the way we are going to conduct the experiment. So at different input level, different input, we get readings. So actually this is xo is our indicated reading or measured. This is measured value. This measured value. This is the xi is our theoretical one. Yeah. This is theoretical, which is shown by our standard instrument, and xo is measured, that is shown by our instrument under steady. And when we have this, say it may be 0 bar, this may be 10 bar, 20 bar, 30 bar, 40 bar, it may be like this. When 10 bar, then reading lies somewhere here, 20 bar reading lies here, 30 bar reading lies there, so 40 bar may be lying there. Suppose readings of the instrument under steady varies like that, then you will find what is the maximum deviation for the different inputs. And here you find the last reading has got maximum deviation from the theoretical value. This is supposed to indicate this point, but it is say instead of 40 it shows some say 45, something like that. So so from the points are lying not on the line linear, that is line means the linear characteristics of the instrument, they are away from the linear characteristics. The nonlinearity represents deviation from the linear characteristic of the instrument, and that is the for an instrument where is the maximum nonlinearity. So here if a nonlinearity is equal to maximum, so we will say the definition is nonlinearity is equal to x measured minus x theoretical. Actually this is theoretically should be here, x theoretical divided by full scale reading. Nonlinearity always referred, you find full scale reading plus or minus, this is maximum deviation into 100 percentage. That is how it is defined, nonlinearity. Now here it is, this maximum deviation is here, this divided by full scale reading into 100. Suppose full scale reading is 100, it itself may be 100, full scale reading may be is equal to 100 bar, and this maximum deviation may be is equal to 5 bar. So here in this case particular instrument nonlinearity is equal to plus or minus 5 bar. So here it may be 2, here also 2, here 1 bar, whatever it is. So 5 bar is the maximum deviation divided by full scale of the instrument. The instrument scale is here. So 0 bar, this is 100 bar. So this is the maximum full scale reading of the instrument, 100 bar. That's what you are supposed to put into 100 into 100, that is percentage, plus or minus. So it is equal to plus or minus 5%. You have to write whenever you are using the full scale reading for the definition, always write plus or minus 5% full scale reading. If you don't write that full scale FSR, then it means plus or minus 5% of the reading itself, x theoretical value. Otherwise, when you use FSR as the basis, write here all in specification plus or minus 5% FSR. That's why you will find many instruments when the manufacturer supplies the catalog, he writes nonlinearity is equal to plus or minus 5% FSR. Always you have to add the word FSR. We have to be careful whenever the nonlinearity is given in terms of FSR. We have to be careful. Before that, we will see there is some commonality, similarity between the readings, between the definitions of inaccuracy and nonlinearity. What is inaccuracy? X measured minus x theoretical. Here also x measured minus x theoretical. Both are same. You find both of them indicate the maximum deviation of the measured value from theoretical value. So you find for an instrument when nonlinearity is given, inaccuracy will not be given. When inaccuracy is given, nonlinearity will not be given. Any one of them will be indicated. Why it is like that? For linear instruments, most of the monitoring type of instruments exhibiting the value, they are monitoring type of instruments. Nonlinear, they will be linear instruments, they will be linear in characteristics. Yeah? The scale will be uniformly distributed. Distance between two consecutive readings will be same, that is linear scale. And there are instruments, for example, flyball speed measuring instrument using flyball principle, you find they will be crowded at the near out the full scale value. I mean near out the end of the scale, it will not be uniform. They are the nonlinear instruments. For nonlinear instruments, the inaccuracy is given. For linear instruments, nonlinearity is given. That is how these two things are made use of. And now, when it is given in terms of full scale reading, we have to be careful. We are not supposed to use such an instrument where it is given the nonlinearity in terms of full scale reading near about the zero point of the instrument. We are not supposed to use the instruments. Why it is like that? Suppose the full scale reading is equal to say 100 bar in a given pressure gauge, full scale reading is 100 bar. On nonlinearity, it is given as nonlinearity for that instrument is equal to plus or minus 2%, say 2% full scale reading. This is what manufacturer has written. Can I use this instrument to measure a pressure of say 10 bar? Can I use it? 10 bar. Can I use this instrument to measure a 10 bar? What is the effect? If I use the instrument to measure a 10 bar pressure, the effect is the error in the 10 bar is equal to 2 bar. Error in 10 bar, error is 2, because 2% of full scale reading is 2 bar. Full scale reading is 100. So 2 by
100 into 100. So 2 bar will be the error for any reading. That is what it meant by whenever we say error is in terms of full scale reading, the error is constant for any reading within the instrument, within the range of the instrument. It remains constant. 2% of the full scale reading. So 2 bar will be the error for any reading. So for 10 bar, the error is error is error. So inaccuracy inaccuracy we can also call it error. Yeah, error in percentage. Error is equal to plus or minus 2 by 2 bar is the error divided by in terms of relative error. So 10 into 100 percentage. Error in percentage is equal to this much. So you will find 20% is the error. Yeah, plus or minus 20%. If I use the instrument to read a reading of 10 bar, error is already 2 bar. So it amounts to 20% error. The 10 bar reading will have an inaccuracy of 20%. Such a large error people may not accept. So using that instrument having a 100 bar as maximum reading, it's not correct to use a very low pressure. Then what we should do? We should use such instrument always above the value of half of the full scale reading. So if you use the instrument say 50 and above, so suppose if you use the instrument for 50 bar, then what is the error? It becomes 4%. Same instrument, when we use it for reading a 50 bar, then in 50 bar error is 2 bar, so it becomes plus some 4%. So when the input signal is larger and larger, actual error of that reading is smaller and smaller. And when we use it for reading 100 bar, then it becomes 2% only. So it reduces like that. Suppose we are using to make a reading for 2 bar, when the pressure is 2 bar, and we use this instrument to read the 2 bar, then error is 2 by 2 into 100. So it's equal to 100% error. It means if I use this 2% full scale reading instrument to read a pressure of 2 bar, the reading of that the error of that reading is 100% inaccurate. So such a way we should not use the instrument. This is on many people do not note this importance. Whenever the inaccuracy or nonlinearity is given in terms of full scale reading, take care such an instrument is used to read the pressure or to read the input signal above say half of the full scale of the instrument. Then only the reading of that instrument will be having sufficient accuracy. So this is regarding linearity. Next one. The next concept is zero drift. This means the pointer has shifted from 0. In other words, drifted away from 0. That's called that's called zero drift. Why it happens? During usage of an instrument for number of years. For example, we have seen the screw gauge. We have got fixed anvil, and this is a moving anvil. Yeah, and this is instrument. Yeah, this is an instrument, and we are supposed to bring and check whether there is any zero drift in a screw gauge. This is screw gauge. And suppose screw gauge we are using it for number of years, and is repeated bringing together, you will find there is some wear may take place. Due to wear and tear, you find some portion of the anvil has been worn out. So when you bring it to make it contact with this fixed anvil, this is a moving anvil. This is fixed anvil. Yeah, fixed one. When the moving anvil is brought to touch this fixed anvil, the reading in the instrument should be 0. This is ideal case, but you will find due to wear and tear, it rotates some more graduations, and then you find there is zero drift in the instrument. When it is brought to contact, zero is not indicated, so it is below 0. So when we use an instrument, this instrument to read the diameter, to take reading of a diameter of a workpiece, what you are supposed to do before bringing the workpiece, bring this anvil and make it touch the fixed anvil, note down the reading. Probably it may be
2 or 3 divisions. So 3 division represents 0.03 millimeter, because 1 division in such a micrometer is 0.01 mm. So 3 divisions it is below. So that means 0.03 mm you have to add. So you take the reading after putting this piece, whatever the reading, add this 0.03 mm to get the correct diameter of the piece. That is zero drift. This actually is your zero drift. This is your zero drift. It has taken place. This is to be added because it is due to wear and tear. Similarly, in some instruments, when the input signal is 0, the instrument may be showing some reading, and actually input is 0. So what we are supposed to do, take that reading, add to the reading, later reading, or subtract depending upon the position of the pointer, whether it has come below 0 or it is above 0. If it is above 0, when 0 input signal, the reading is say 2 bar, and later on you will find any reading, subtract this 2 bar, then you will get the correct reading. So that is called zero drift. That is, this instrument has drifted away from 0 position. That is zero drift, and that is due to wear and tear and some shift in the elements. Now next concept is sensitivity drift. Sensitivity drift. We know what is sensitivity. Sensitivity is equal to, if it is S, dxo by dxi. Yeah, that is our sensitivity. Dxo by dxi. That is our sensitivity. Is equal to, for that piston and cylinder type pressure gauge, it is equal to A by Cs into B by A. We have defined what is A, Cs, B by A and all. If you remember, A represents the area of the piston, Cs is the spring constant of the spring, and B by A is the ratio, lever ratio of the pointer for that piston and cylinder type pressure gauge. So for that instrument, sensitivity is equal to A by Cs and B by A. And we have seen sensitivity remains constant throughout the working range of the instrument. But suppose some atmospheric change has taken place, and it may affect any one of these parameters. Now since sensitivity is dependent on this parameter, when this parameter is changed due to some other reason, then sensitivity changes. That is, it has drifted from its original value. For example, in the same instrument, suppose temperature of the pressure gauge in the working condition, temperature of the working atmospheric conditions where the instrument is used, has increased from the calibrated conditions. So from 30 probably it has gone to 40. Due to this higher increase in temperature, you find the spring constant reduces. Yeah. Spring constant reduces when the operating temperature is higher. In atmospheric condition in which the instrument is used, when the temperature increases, Cs reduce because the spring material becomes softer at higher temperature. So when it is softer, what will happen? Or for a given force, it will deform more. So that means for a given pressure, now since the temperature is higher, since the spring has become softer, it is giving more deformation, or Cs is affected. So sensitivity has drifted from S to S dash. That is what we see in a graph. So this is your say Xi, this is your Xo, and this is original S, this is your S, and now due to temperature change, it has drifted to S dash, S dash. So now what is the effect of S dash? For any given any input, instead of reading being XO1, it is being XO dash, XO dash, XO star for example, XO1 star. So you find the error will be more and more for higher and higher input values because of sensitivity drift. Sensitivity drift affects the error very much, and its magnitude will be depending upon the input value. So lower the input signal, smaller will be the error. So it gives varying error for the input. If there is any sensitivity drift, it will give rise to varying error in the instrument functioning. We should avoid. That's why we are supposed to use the instruments in the controlled conditions which the manufacturer mentioned. We use the instruments between plus 20 to plus 40. Beyond the range, if you use, then the error depends upon the value of the input signal in this particular case, or it may vary at different situations. That is our sensitivity drift. So we have seen all the important concepts, and there is some interrelation between some of the concepts. That is, first we will take relation between sensitivity and least count. we know individually what is sensitivity, what is least count. But what is the relation between these two things? Therefore, to understand that, let us see these instruments, two instruments. One instrument is like this, another instrument like that. That is our xi, xo. Two instruments, instrument 1 and instrument 2. Now, one instrument has got, that is this is S1, that is S1, and this is your S2. S2. The sensitivity for second instrument naturally is larger than sensitivity for the first instrument. And in this case, suppose I give a small change in xi, say delta xi is the change in the input signal. Simultaneously, I am giving input signal for both the instruments, and I note down the reaction of the instruments. Now, this instrument represents an output of say 1 mm or say 1.5 mm. I say 1.5 mm. This x output is, this is pressure Pascal, and the output signal is in terms of millimeter. So, for first instrument, for a delta xi may be 1 bar. Okay. For 1 bar change, the first instrument gives a displacement of the pointer in its scale to an extent of 1.5 mm. The second instrument deflects to a distance of say 3 mm. It reflects to a distance of 3 mm. Now, there is a standard in international practice. The distance between two graduations should not be less than 1.5 mm. So, it can be 1.5 mm or more in a scale. The distance between two consecutive graduations should not be less than 1.5 mm. That is what is that will make the person who reads this who takes reading in the scale, his eyes will be less strained if the distance are 1.5 or more. If it is smaller, you can make reading, but if you take repeated reading, your eye will start aching after some time. To avoid this, all countries have agreed the distance between two graduations in scale should not be less than 1.5 mm. So, in this case, what happens, since for 1 bar it has given 3 mm, I can have 2 graduations of 1.5 mm. So, least count here it can be 0.5 bar. For 1 bar it has moved 3 mm and it can be divided into 2. So, 0.5 bar is the least count. Least count for a second instrument, it can be 5 bar, 0.5 bar, because for 0.5 bar itself I got 1.5 mm. Less than that means the graduation distance will reduce, I cannot do. That means higher the sensitivity, lower can or finer can be the least count. That is the relationship between sensitivity and least count. For higher sensitivity instruments, we can have finer least count. If the sensitivity is smaller, then we cannot have a finer least count, because there is an understanding the distance between the two graduations should not be less than 1.5 mm. The second relationship is the inaccuracy and the least count. Second, the relation between sensitivity, least count and or inaccuracy, relation between inaccuracy and least count. What is the relation between inaccuracy and least count? Now, the manufacturer is supposed to give us the pamphlet for any instrument we purchase, and in course of number of years we have misplaced the pamphlet. What we should do? We don't have the pamphlet where we can refer what is the inaccuracy or nonlinearity of the instrument. We don't have. That book has been lost. In such instances, what is recommended is see the least count of the instrument is equal to the make it inaccuracy. That is how the instruments are designed. The least count is made. The inaccuracy, if we find the sources of inaccuracy, add all the inaccuracies, and you will get a certain amount of inaccuracy. Say probably here I got 0.5 bar as the inaccuracy for that particular pressure gauge. Then least count, make that maximum inaccuracy itself as least count. This is the principle normally adopted by all manufacturers throughout the world. So, in case you have lost the pamphlet, don't bother.
find out what is the least count of the instrument, make that least count itself as inaccuracy. So, for this instrument with a least count of 0.5 bar, inaccuracy is also is equal to plus or minus 0.5 bar. This is the norms which we have to adopt in designing of instruments. Suppose inaccuracy is 0.5 bar, which you have found, the designer has found out. Can he have a smaller least count, say 0.25 bar? Yeah, that is inaccuracy is inaccuracy is equal to 0.5 bar, but least count is equal to 2.4. Is it permitted? Is it all right? Yeah, can we have like that? It's not permitted, because when inaccuracy is error is 0.5 bar, dividing the error, reading within the error is not permitted. It doesn't give there is no sense if you read below the inaccuracy. Hence you find least, even though we can have finer and finer least count. Simple way of achieving finer least count is increase the pointer length to any length you require, and you can have very fine least count. But that is not permitted, because inaccuracy is much larger. If you get if you can have a larger, finer least count, though it is possible, it is not permitted. Hence, you cannot increase the length of the pointer alone as you like, because inaccuracy is larger after certain increase of the length. So, that is the limit for the increasing the or getting the finer least count. It puts a limit. Inaccuracy within the instrument puts a limit for the least count. I think with this we can close it today. Yeah.